Yes, hello there. My name is Macklin Lengeli, and I'm going to take you through model selection and deployment, plus the different architectures we shall be having for our different models that we based on to make our comparisons. So we are working on an AI scalp detection system, and for that case, we have to select which model we are going to use to train with our data so that we can be able to have the predictions of the scalp images. So model selection is a key stage in machine learning because the success of a project depends greatly on choosing an algorithm that matches the nature of the data and the problem. We have to look at the nature of our data set. We also have to look at the problem being solved. Is this model solving the problems we are having, and does how will it work with our data set? So we are putting all those factors into consideration. So the main focus was on faster RCNN and YOLO V8, which YOLO is only look once, since both are widely used in object detection but differ in speed. So basically, object detection, we are looking at the fact that in case we feed an image into the model, then it will have to detect different objects in these scalps, and these objects would be meaning the different regions having the different scalp conditions. So these two models differ in speed, complexity, and detection strategy. So the purpose of this comparison was to identify the model that offers the best balance between performance and practicality for our data set. So talking of the models, we have faster RCNN model. So this one is a two-stage object detection architecture designed to detect objects more accurately by first generating candidate regions and then classifying them. So this one gives us the two stages in the faster RCNN. First of all, it will be the classification, which classification will be done by identifying or marking the suspected regions of the suspected regions having the scalp conditions. Then after identifying those regions or proposing those regions, then it will have to classify them. Then after classification, that is when it shall have to make its predictions. So in this project, it is used to detect scalp condition regions in images and assign them to disease classes such as dandruff, psoriasis, folliculitis, and alopecia. So the architecture of the faster RCNN is suitable for detailed region-based detection because it separates proposal generation from final classification. So this is what we talked about. Faster RCNN is a two-stage, and for the fact that it is a two-stage, it critically looks at the regions first before making predictions. After looking at the images, it is going to analyze them. Then after analyzing the images, it is going to give decisions or to give predictions basing on the criticalities it has done during the classification. So this is the faster RCNN architecture. It begins with the input layer where the scalp image is fed into the model. Then the image passes through the backbone convolution layers. So this is the visualization or the diagram for the faster RCNN architecture diagram. So from this, we are seeing the input layer. So this is where the scalp image is fed or uploaded, is fed into our model. So this scalp image, remember in our data set, we're having different images which are varying in sizes and in different sizes, and maybe basically we are looking at sizes here. So here in the input layer, we input or we upload a resized image, whereby in basically what we mean here is that we have to first resize them to a given to a standard size whereby they are all having the same size. So those images are fed into the model through the input layer. Then these models move to the backbone CNN layer. So at this layer, this is where we're having feature extraction. So when you're talking of feature extraction, we mean the flex we'll be having on the scalp. That is to say that tiny dandruffs or the dandruffs which are just developing. We can talk of maybe the texture, then also the different patterns we'll be having, then the lesions and the hair density changes. So after that, we're having the third layer, which is the region proposal network. So basically, this one proposes, it is where the model proposes regions of the different conditions of the scalp. So it suggests possible object regions, finds candidate scalp condition areas, and proposes where the disease may exist. So as long as the model suspects a given area or a given region on the scalp have to be having a given scalp condition, then it will mark that area or it will mark that region. So after marking that region, we shall move to the next layer, which is the ROI. This is called the region of interest pooling. So after classifying or marking the suspected regions to be having scalp conditions, we have region of interest whereby these regions are standardized or normalized. In other words, they are put to a given size so that they all be of the same size, and they are normalized so that they can be easily worked or analyzed by the classifier plus big box regress, and that is the next layer. So in this layer, they predict condition class. Remember, in the region of interest, the regions were normalized and they are put in our state that they can be easily be brought up for analysis by the next layer. So this next layer, which is the big box regressor, it is going to predict the condition class from these regions, and it will refine the box coordinates. Of course, these box coordinates will be the boundaries of the region of the object region, and it will also output the confidence score. Then afterwards, finally, we shall have the final output, and this is where we are going to show, or where we are going to see the bounding boxes. So that means the the region having the scalp condition, you shall have the condition labels. For example, if you're having maybe a given a region with a scalp condition, it will be labeled maybe dandruff, if it is an area having dandruff or affected by dandruff. Then we shall have the confidence scores. This basically mean how sure are we with the results we've gotten. If it is up to 80 or 90% as a confidence score, call it say 0.9, then a trichologist will be very sure that this person is affected by that plus condition or by that disease. So our next slide, we're having the YOLO V8N model. So this one is that you only look once model. So it is a lightweight nanovariant, Ultralytics YOLO V8. For the fact that we're having YOLO V8N, the N means it stands for nanovariant, and in nanovariant we mean that it is a lightweight model. It is lightweight and very efficient, and this makes it ideal for real-time scalp health screening on mobile, call them edge devices in resource-limited settings. So in our model, as we are going to go about with our training, we initially had the hair analysis dataset, and this dataset had to be converted or changed to annotations. Then these annotations were changed to the YOLO format, and hence getting the .txt files. So this dataset was then organized into training, validation, and test states, and the model was trained to detect and classify affected scalp regions. So the performance of the model was then evaluated using metrics such as precision, recall, MAP50 and MAP59 to 95, and this is the stricter one. So as we shall see in the screenshots of the interfaces, we shall see the performance of our model. So the architecture of the YOLO V8, as the way it is for the faster RCNA, it also has an input layer, and this is where the image is fed into the model. So obviously we had to standardize it. We had to standardize the images by giving them a 640 by 640 size. Then after uploading the image or feeding the image into the input layer, through the input layer, we move to the backbone layer, whereby we have the feature extraction, which is the same as the other side of the faster RCNN. So during feature extraction, that is where we are going to look at what texture we have in the texture of the hair, the redness of the scalp, and maybe the lesion, the flakes, are they there on the scalp or not? So in the backbone we're having, it also has layers. There is the conv layer, and this is called a convolution layer. It is used to detect the simple patterns. For example, the edges, maybe the small flakes on the scalp. We also have the C2F layer, and this one for it helps the model or the backbone, the model through the backbone layer to be able to learn deeper and richer image patterns for the images. Then we also have the SPPF layer. This one helps the model to learn patterns from of a wider surrounding or of a wider area. So after the backbone, after feature extraction, we moved to the neck layer, and this is where we're having feature fusion. Feature fusion, we made that it gets a collection of the different features from the different levels. So the features from the backbone layer, the features from the different other layers, they are all combined at this step. Then it also has the concat with PF, the C2F also is here, and also the downsample. So from the neck layer, we move on to the detection head, and this one is it gives us the final output for the YOLO V8 architecture. So here we are going to detect the small, the medium, and the large scalp regions or large scalp conditions. So basically that is the YOLO V8 architecture. So okay. So YOLO V8 first receives the scalp image as input, then the backbone extracts visual features using convolution and C2F blocks, while CPPF captures wider context, and that's what we said. So the neck then fuses features from different scales, so the model can detect both small and large scalp condition regions. So finally, the detected outputs, bounding boxes, confidence scores, and predictions for the 9 scalp condition classes in our dataset. We are basically working with 9 classes of the scalp conditions. So talking of the YOLO V8 deployment pipeline, because it is what we had to select after all the comparisons. We had the hair analysis dataset, and this one includes images, scalp images, having the dandruff, psoriasis, alopecia, and other scalp conditions, and these images are annotated. So these after annotation, of course, we had to convert these files into the YOLO format, call them the .txt files. So afterwards, we fed that dataset into the model, taking us to the training phase. So as we are training, we had to fine tune the YOLO V8 model using that data set. So after training the model, we chose one with the best land weights after training and validation, and we saved it as best.pt. So this trained model is then converted to YOLO V8, is then converted to a TensorFlow Lite format using Ultralytics. So basically this format makes it easy for deployment. So on conversion, we get a TF Lite model file, and this file, it is a lightweight model optimized for mobile development, as we've said. So after that, we can export this file into a mobile app, taking us to the mobile app phase. So then we can develop our mobile app using Flutter. And Flutter helps us to have a code base which can work on both iOS and Android. So as we're having the mobile app, basically, it means that a trichologist has an interface on which or through which they can upload the scalp images from their patients. So this takes us into the image acquisition phase. So trichologist can be having the camera or a phone or using anything as long as it inputs the scalp image, then captures the image or can even remove the image from the gallery. Then when the image is uploaded, we shall have the pre-processing, of course, through as we are using the app. So in pre-processing, the image is resized and normalized to match the YOLO V8 input size. Then we're having the TF Lite interpreter, which runs on the device. It runs on device real-time inference, meaning that as it helps us to have real-time results. As soon as the image is uploaded, we can have the processing. It is looked at once, then we can be able to get the prediction. So this TF Lite interpreter runs on device real-time inference. Then we shall have the post-processing, which involves confidence filtering, bounding box selection, and class label extraction. Finally, we shall have the app output, whereby the results are displayed to the trichologist through the mobile app. So in this output, we have the bounding boxes, labels, confidence scores displayed on the scalp image. So basically, that is the YOLO V8 deployment pipeline. Then this explains the pipeline converted. The app processes the image, runs inference locally using the TF Lite interpreter, applies post-processing to refine detections, and finally displays bounding boxes, disease labels, and confidence scores in real time. So we are talking about model selection. We are done looking at the faster RCNN and also the YOLO V8. So we want to make a comparison between them so that we can choose the best for our project or our AI scalp detection system. So the important architectural difference is that faster RCNN is a 2-stage while YOLO V8 is a 1-stage. So basically, faster RCNN is very good if we're having if we need object detailed results, and if the results are not that urgent and we don't need them in real time, faster RCNN can work very, very good for that, which is otherwise for YOLO V8, because for it is a 1-stage. It only looks once at the image and gives you a prediction there, and then making it very fast and very suitable for real-time systems. So faster RCNN first proposes the regions, then classifies them. And for that case, it makes it a 2-stage detection model. Then for YOLO V8, it predicts boxes and classes in a single forward pass using backbone, neck, and detection head. So faster RCNN was extremely slow to train on my machine, basically, because I was running it on a CPU. And maybe if someone used a GPU via Kaggle or via Google Colab, it would have been way much, it would have trained for lesser hours. Though it doesn't remove the fact that it's trained so slow than YOLO V8. YOLO V8 was so fast and during training, and this made it a more workable option. So justification, you're having the technical justification whereby YOLO is fast enough to give instant results during a consultation, small and tough enough to run fully offline with everyday phones in rural areas with no Wi-Fi. So YOLO V8 is it is a very good model, and we chose this in consideration of a case. Let's say a patient moves into a hospital and meets a trichologist. Then the diagnosis is taken, the scalp condition, the scalp images are taken, and afterwards the trichologist starts looking for maybe Wi-Fi or internet connection, and this would cause a delay, and it would cause a delay in getting the results by the patients. So that's where YOLO V8 comes in a way that it in case after deployment, we shall not need the Wi-Fi, we shall not need the internet connections. It will work fully on offline and also very fast, and it does not need a lot of hardware. So that is why that makes it reliable and practical for nurses and clinics where resources are limited, helping in the catch of scalp issues early without needing fancy equipment or constant internet. Then for the scientific justification, YOLO V8 has been proven. It has a scientific backing in dermatology and tricology tasks as being successful. So its multi-scale design excels at detecting both tiny microscopic features and larger macroscopic lesions in the same image. So this one makes it better than other YOLO versions. For example, the YOLO V10 and YOLO V11 cannot easily detect the small lesions. For example, if you're having tiny flakes or the starting dandruffs on the scalp, and maybe even other bigger images, YOLO V8 is very suitable for detecting these scalp regions, unlike other versions or other models. Even the faster RCNN, although faster RCNN would have done it, though it would be slower and it would give delayed results. So we're having these are the screenshots of the interfaces. These were the classes we used: alopecia areata, then contact dermatitis, dandruff, folliculitis, the headlights, the low hair density, and also the psoriasis. Then these are class-wise metrics. So that was what I had. Thank you for listening. Thank you for listening.